Just open your presentation, then move to Zoom screen. Oh,
I think finally it worked.
brilliant.
I'm sorry, it's
Thank
just
you.
that I have I had a new Zoom, and because of this, didn't want it to work. Okay, I hope now it's visible.
Yeah, it's okay.
So far. Is it okay?
Yeah, it's okay.
Great. Thank you. And thank you very much for the invitation. I'm deeply grateful for it and very honored to be a speaker here in the Ukrainian conference. And so I talk about Gaudin's algebras. So it's an interplay between something in the symmetric and enveloping algebra of Lie algebra. So Q for the moment is any even infinite dimensional. So the ground field of characteristic 0, and we have the symmetric and the enveloping algebras of Q. So the enveloping algebra has a natural filtration by, let's say, degree of an element coming from the tensor algebra. And if we consider the associated graded, then this is by Poincaré-Birkhoff-Witt theorem, the symmetric algebra. So enveloping is non-commutative, but it's, well, commutative up to degree -1, so to say. And from this, we can obtain a Poisson bracket on the symmetric algebra. So just by taking the commutator here on the right-hand side, and this will be a Poisson bracket between the cosets. It can be defined also so for Lie algebra, just a commutator, and when we extend it by the Leibniz rule to the whole symmetric algebra. And there is also a geometric definition. So we take differentials at a point gamma, a point from the dual of a Lie algebra. So the differential will be an element of a Lie algebra. So we can compute the commutator between them, and we can evaluate gamma at this commutator. So this will be the value of a Poisson bracket between functions f1 and f2 at a point gamma. And if Q is finite dimensional, then the symmetric algebra is just the algebra of polynomial functions on the dual space. So in that case, we will have geometry, finite dimensional Poisson variety. It's a very well-studied object. Now, what does it mean to be commutative? You all know. Poisson commutative means that the Poisson bracket vanishes on some subalgebra. Or we say the two elements Poisson commute if the bracket between them is 0. And well, because the bracket comes from the enveloping algebra, if I start with something commutative here in U of Q, and take a subspace in the symmetric algebra generated by all symbols of elements from C, then this subalgebra will be Poisson commutative. So the bracket will completely vanish in it. So I'll repeat the statement. Well, here above in yellow. So this is one source of Poisson commutative subalgebras in the symmetric algebra. So it may look a bit ridiculous because we're starting from a difficult object and looking there for something commutative, which may be difficult. But we will see later that some of these objects, they do appear in this way. So sometimes it's actually easier to work with enveloping algebra than with symmetric algebra. And another one, which is much more classical and much more direct. So this is something for Poisson varieties. So if we have two compatible Poisson brackets, I'll explain later what it means, we can construct associated Poisson commutative subalgebra. So apart from this, there are certain other advantages of going to the commutative object. So first of all, there is a geometric machinery, geometric methods for dealing with it. In particular, for the Poisson commutative subalgebras we are going to obtain. So the coadjoint orbits are symplectic varieties. So here we have methods of symplectic geometry. And we can also use commutative algebra because symmetric algebra is a commutative object. So for instance, it's quite easy to see that the transcendence degree of a Poisson commutative algebra is bounded by a certain number B of Q, which is 1/2 of the sum dimension of Q and the index. So here's the definition of the index. It's a codimension of generic coadjoint orbit. So gamma is point in the dual space. Q is a Lie algebra Lie group corresponding to Q. So this is a coadjoint orbit, and I take the maximal possible dimension of a coadjoint orbit, meaning I'm taking a generic object, a generic orbit. And from this, one can deduce that also transcendence degree of a commutative subalgebra of U of Q is bounded by the same number. And this is rather difficult to see directly because we cannot pass the differentials. This is not commutative object, and actually even transcendence degree for any subalgebra of U of Q is not well defined, so we have to take Gelfand-Kirillov dimension. So only if it is a commutative algebra we can talk really about transcendence degree. Okay, so in the title you have seen Gaudin subalgebras. So what are they? The name comes from the Gaudin model. This is something appearing first in 1976 with motivation from physics. So completely integrable quantum spin chain, it's called sometimes. And in algebraic terms, this model roughly consists of n quadratic Hamiltonians. So here are the formulas. So I'm assuming now that Q is G is semi-simple. So I take direct the sum of n copies of G. This is a semi-simple Lie algebra H. So on G, the Killing form is non-degenerate, so we can find an orthonormal basis with respect to it. And then because I have n copies of G, I have n copies for each element of a basis corresponding to the copies on G in the direct sum. So xi, with k in the brackets above, this is a copy of xi sitting in the case direct summand of H. So, and then, so to say, we can take this invariant pairing between the i's and the k's and the j's copies of G. And then we also need a vector of different elements from the ground field because we want to divide here by the difference. Okay, so these elements they are quadratic Gaudin Hamiltonians. It can be seen directly by commuting commutators that we commute in the enveloping algebra. I can as well consider these products as elements of a symmetric algebra when we Poisson commute in the symmetric algebra. Well, we're interested in other functions that commute with quadratic Gaudin Hamiltonians. So an observation, so all of them are invariant with respect to the diagonal copy of G. The goal in this Gaudin model is to find eigenvectors of these quadratic Hamiltonians in a finite dimensional representation, which is a tensor product of n irreducible finite dimensional representations of G. And there are some methods for computing with eigenvectors and eigenvalues. So Bethe-Ansatz works very well for SL2, but it does not work quite so well for high-dimensional simple algebras. So in 1994, Fagin, Frankel, and Reshetykhin, they suggested a different approach to this problem of computing eigenvectors and eigenvalues of Gaudin Hamiltonians. So they constructed higher Gaudin Hamiltonians from a huge commutative subalgebra in the enveloping algebra of a nilpotent part of the current algebra. And historically, it's here with T inverse. So we are taking, well, T inverse for reasons of history. We could as well take T. Okay, so this, I'm not going to tell you what this Fagin-Frankel center is, but it's, well, it's a very, very big commutative subalgebra with many applications to quantum and classical integrable systems. So in particular, we can define, following Fagin-Frankel and Reshetykhin, Gaudin subalgebras, where images of a Fagin-Frankel center, and actually we can define them in two different ways. So here at the end of the slide, I have an alternative description, but maybe we'll start with it. So we take, again, a vector of numbers from the ground field, which are pairwise different and non-zero. Let's consider a polynomial in T inverse, where these numbers, inverse of these numbers were zeros of a polynomial, and take quotient. So because the roots are distinct, this quotient of a polynomial ring by P will be a direct sum of one-dimensional submodels, and when the tensor with G is a direct sum of n copies of G. So this will be exactly H. So the reducible algebra is just the image of a Feigen-Frenkel center in the quotient by such a polynomial. Or maybe more difficult, I don't know, easier to understand, difficult, more difficult to write description. We take a diagonal in the tensor product, and we use this map, rho, sorry, this is a misprint, should be Z, a vector Z. So for each copy of G, I take the corresponding element of a ground field. And we will see another thing, how these elements Z1, Zn come into play. So as I told you, the goal was to consider the action of Gaudin Hamiltonians on the tensor products of vector spaces. So we can do it here. So we take again a tensor product of n finite dimensional representations of G. And we can have the enveloping algebra of a current algebra, even loop algebra acting here. So again, for each copy, for each representation Vi here, I choose the corresponding number Zi and replace t to the k by the Zi to the k. So x is an element from G. Tk, well, this is this t, k is negative. So for each sub-representation here, we have its number. So if we define the action of the enveloping algebra in this way, then the Feigen-Frenkel center will act exactly as the Gaudin algebra. And the main fact about this Gaudin algebra constructed in FFR is that it contains all quadratic Hamiltonians, but it also contains elements of higher order. And all of them they have been used for constructing eigenvectors and eigenvalues. So in order to diagonalize the initial quadratic Gaudin Hamiltonians, and actually it also works to some extent. And there is a connection with Knižnik's homological equation in this paper, and also in the whole of this problem. Well, the result of Rybnikov, which was obtained much later, I suppose like 30 years later, which was a conjecture, first proven for GLN, and then by Rybnikov, well, in the generality we know by today. So this Gaudin algebra of Feigen-Frenkel and Reshetykhin, it acts diagonalizably on this tensor product, almost for all values of Z, of a vector Z. If we take it from complex numbers, so his paper is about complex numbers, but we can extend to other fields. And actually it acts diagonalizably and with a simple spectrum for each element from Rn. So for Cn, we have just some open subset, which is difficult to define. It's an existence theorem, but for real numbers, it's actually for any of them. So of course, the assumptions have to stay. So all elements coordinates are non-zero and they're pairwise different. So the goal of this talk is to answer the following question. Is there a pair of compatible Poisson structures on the dual of H that produces the Gaudin algebra, or rather its associated graded image by the Leonard-Magritte scheme? And now I'll tell you what this Leonard-Magritte scheme is. So a bit roughly, I think. So we have two compatible Poisson brackets on one and the same variety on one and the same algebra. So compatible means that their sum is again a Poisson bracket or any linear combination of them for that matter. Okay, so two brackets, we take any linear combination, this is again a Poisson bracket, so we obtain a pencil, two-dimensional vector space of Poisson structures. Then in this pencil, there are regular and singular Poisson structures. So here the definition is in terms of Poisson tensors. But maybe we look at the geometric interpretation. So each Poisson structure has its symplectic leaves, so maximal connected subvarieties, where the restriction of a Poisson structure is non-degenerate, and for each point of the same, of the same rank, so the dimension of a subvariety. So the rank of a Poisson tensor is the dimension of a generic symplectic leaf, And in this pencil, there is an open-dense subset where this genetic dimension of symplectic leaf doesn't change. So it's maximal possible for all Poisson structures in the pencil. Say R. This, yes, this R. And then having regular and singular, we forget about the singular structures and take only the regular. And for each regular structure, we take the so-called Poisson center. So this is the algebra which commutes with everything. And with this Poisson centers of all regular structures, we generate a subalgebra, which is Poisson commutative with respect to all brackets in the pencil. Okay, so it is much easier when we are dealing with the Lie algebra, so-called linear Poisson structure. So the Poisson tensor or bivector can be defined by this formula. So we evaluate it on the differential form. Exterior product of two differentials. This is just a Poisson bracket between the corresponding functions. If we consider the Poisson tensor at a point gamma of a dual space, this is a skew-symmetric form on Q. It has taken the commutator and Lie algebra and evaluating gammaed it. We have already seen it on the first slide. So symplectic leaves of the Lie Poisson structure are coadjoint orbits. Well, assuming that Q is connected. Otherwise, we have to take connected components of coadjoint orbits. So the rank of a Poisson tensor is the maximal dimension of a coadjoint orbit. It's also the maximal rank of its skew-symmetric bilinear forms. And then we also obtain that the index of Q is the dimension of Q minus the rank of a Poisson tensor. So we can interpret index in terms of Poisson structure. And so the Poisson center, as I have told you, this is a subring of functions that commute with everything in the symmetric algebra. But because symmetric algebra is generated by Q, I can put here just elements of this is Q, this is the Lie algebra. And this is known as the ring or subring of symmetric invariants. So the invariance of the Lie algebra Q and the symmetric algebra, and actually I can replace it here by the group Q if Q is connected. Okay. So this Poisson centers of regular structure would generate a subalgebra Z depending on our pair of Poisson brackets. So this is what comes as a result of a Leonard-Magritte. And the question was, is it possible to find something like this for the Gaudin subalgebras? Okay, so the answer is yes. So just repeat a bit of notation. So H is a direct sum of n copies of G. We have this Gaudin subalgebra here. We can consider it associated graded image in the symmetric algebra, and the answer is yes. Actually, there is another linear Poisson bracket. That means that we have a different Lie algebra structure on the same vector space, such that the graded image of the Gaudin subalgebra is exactly this Z, corresponding to our pair of two Poisson structures, or Lie algebra structures on H. So what advantages we are getting? So first of all, we can show using the theorem that the Gaudin subalgebra or its Poisson analog, classical analog, were both maximal with respect to inclusion. So either in the invariance of a diagonal G in the symmetric algebra or in the invariance of G in the enveloping algebra. And we also obtain a new proof for the result of Chervov, Falco, and Rybnikov that the Gaudin subalgebra is a polynomial ring. And it has this number of generators, so n minus 1 divided by 2 times dimension of G, plus n plus 1 divided by 2 rank of G. And this number is a maximal possible value for a transcendence degree of either Poisson commutative subalgebra contained here, and then by the general trick also for a commutative subalgebra contained in the invariant of a diagonal here. So now how do we construct this pair of compatible brackets? So this comes from division with rest, with remainder, sorry, in a polynomial ring. So again, I'm going to consider the current algebra, and now we can replace T inverse by T. That's more convenient. So I take a monic polynomial of degree n, and I consider the quotient of the current algebra by this polynomial P. So this is Q, tensor with a quotient of a polynomial ring. So as a vector space, it is a direct sum of n copies of Q. So each of them corresponds to T bar to the power K, starting from 0 and ending with n minus 1. And the polynomial P defines a Lie bracket on this vector space, because it's a quotient of a Lie algebra by P. And actually, in the down-to-earth terms, we just take elements where we have powers of T, we take the usual commutator, as in the current algebra, and then we divide by P with a remainder, and the remainder is what interests us. So in particular example, P is T to the power n, we will obtain a truncated current algebra, also known as a generalized Takeeff algebra modeled on Q, that have notation for it. And it's easy to describe the corresponding Lie bracket. So I take a Lie bracket in Q between two elements. And then for the power of T, this is A plus B. And if it is still smaller than n, then it just remains here. This is an element somewhere in this direct sum. And if it is larger than or equal to n, the commutator is just 0. And then quite a nice thing, we have a following proposition. If we take two monic polynomials which differ either by a constant or by a term, by a linear term, so the degree of a difference is not larger than 1, different polynomials, then the corresponding Lie brackets are actually compatible. So the Lie brackets on this vector space, the Lie algebra structure is complicated, so it's difficult to write it directly. We have to know the polynomial. But we can still conclude that they are compatible in this case. And actually, we can see it directly. So I take a sum here with two coefficients such that the sum is 1. This is enough. And then I'm just adding the polynomials. So the sum of these two polynomials will be, again, a monic polynomial of degree n. Okay, so we have two compatible Poisson brackets, and this is independent of Q. It works also if Q is infinite dimensional. So then again, we can describe this quotient by P quite explicitly. So the quotient of a polynomial ring, so it will depend on the multiplicities of the roots of our polynomial. And well, just looking at the roots, we will see that the quotient of a current algebra will be a direct sum of a Takeeff Lie algebras. So it doesn't really matter if I take a quotient by t to the k or t minus a to the k with just a change of variable. So with Lie algebras appearing here, we're just direct sum of Takeeff Lie algebras. And then again, in a particular case, when all roots of a polynomial are distinct, pairwise distinct, we will get a direct sum of copies of Q, of n copies of Q, because Q, Takeeff Lie algebra corresponding to 1 is just isomorphic to Q. So current algebra, a quotient of a current algebra by T, not just Q. So actually we can write them explicitly, as you see in this example. So we can find this n copies of Q very, very explicitly in this quotient. And then in particular, if we start with a semi-simple Lie algebra G, then the quotient will be semi-simple. So this will be a direct sum of n copies of G. So exactly our H in the Gaudin model. And then another thing, an old result of Raïs and Tavel tells us that the index of a Takeeff Lie algebra is actually the same as the index of the direct sum of n copies of Q. So n times the index of Q. So from this result, we can see that index of any Lie algebra associated with P is the same as the index of direct sum of n copies of Q. So for all Lie algebras that appear here, the index is the same. So this allows us to describe regular and singular structures in the pencil generated by two polynomials. So whatever is really given by a polynomial will be regular, and the only singular one will be the difference of these two Poisson brackets. This one will be singular, and there is here an example. So I take two polynomials that differ just by the constant term, so tn minus 1 and t to the power n. And so the singular line is the difference, and in that case we obtain not a Takeeff Lie algebra, but something different. So I take here positive part, strictly positive part of the current algebra, and take the quotient by the t to the power n plus 1. So the index actually jumped. This is a singular point, all other points are regular. So by the Leonard-Malgry scheme, we take regular points, and for all regular points, the Lie algebra is a direct sum of Takif-Lie algebras. So we need symmetric invariance of Takif algebras, and they are quite well understood. So from this understanding of the invariance of Takif-Lie algebras, we can obtain a more explicit statement than in the previous theorem. So exactly if I take P with the roots A1, AN, take the inverses, then the algebra associated to P and P plus T, this is the Gaudin subalgebra corresponding to Z. And if I take, the same roots, but for polynomials P and P plus 1, as in the previous example, then we get the associated gradient of a Gaudin subalgebra for Hamiltonians which have A1 until AN in place of Z1, Zn. So basically, these are main examples. So whatever we take, we get a certain Gaudin subalgebra, or rather Poisson analog of a Gaudin subalgebra. Right, I think that's it. Thank you very much for your attention, and slava Ukraini.